Welcome to our presentation about efficient multi-way merge algorithm implementation using a min heap for optimized data merging. Our presentation will walk you through the core concept behind multi-way merging, the rule of min heap in minimizing time complexity, and the real-world application, where this optimization can lead to the measurable improvements, particularly in the external sorting, database, and big data processing. Before we begin, allow us to introduce ourselves, the team behind this project. I am Angelica Aquino and I will be leading today's discussion focusing in understanding the efficient multi-way merge algorithm using a min heap.
Hi, I'm Krizia Mae F Funiestas, and I'll be discussing the implementation of the multi-way merge algorithm using a min heap for optimized data merging.
I am Daisy and I'm Magno, the creator of this PowerPoint presentation, and today I will be discussing the key advantages of the efficient multi-way merge algorithm that uses a min heap structure.
And I am Rhonielyn Mhei Tolentino, and I will be the one to discuss the performance analysis of efficient multi-pair merge using min-heap up to the conclusion.
Understanding the efficient multi-way merge algorithm using a min heap. First is the efficient data merging. When you have lots of sorted data split across different files or streams, like logs from different servers or chunks of sorted database records, you need a way to combine them all into one big sorted list. That's where multi-way merging comes in. Instead of merging two files at a time, it merges many at once, which saves time and computing resources. Next is the enhanced sorting performance. Sorting becomes much faster, especially when we're dealing with external sorting. That's when your data is too big to fit into your computer's memory. So it has to read and write from a hard drive. Multi-way merge using a min heap reduce the number of passes needed over the data, which means faster sorting and less waiting. The third one is the memory and input-output optimization. Reading form and writing to hard drive is much slower than working memory. The multi-way merge algorithm with a min heap designed to work keep only smallest possible data in memory and read new data only when needed. This smart way working means your computer doesn't waste memory or keep going back and forth to the disk, leading to the faster and more efficient processing. The last one is the critical for data system. Modern systems from big data platforms like Hadoop to databases like MySQL to file systems all rely on efficient data merging. When you're dealing with terabytes of data, even smallest efficiency add up quickly. A well-implemented way merging with min-heap ensures in smooth, scalable performance, especially during operation like sorting, query, or aggregating data in analytics pipeline. Now, let's proceed to the common uses cases of multi-way merge algorithm using a min heap. The external sorting, database merging, big data analytics, and searching engine index. Introduction to efficient multi-way merge using a min heap. What is the efficient multi-way merge algorithm? This technique is all about efficiently merging several sorted datasets into one big sorted list. And it does that using something called a min heap. A min heap is a special kind of data structure that always keeps the smallest item at the top. So when you're merging, it helps you quickly find the smallest next value all the sorted files or streams you're working with without checking every single one manually. By using a min heap, this method becomes much faster and less demanding on your computer's memory. It also cuts down the number of times your system has to read or write to the disk, which super helpful when working with massive datasets like those that don't fit in memory. That's why it's widely used in external sorting, database operation, and big data analytics, places where merging huge amount of sorted data in regular and critical tasks.
Key advantages of the efficient multi-way merge algorithm using a min heap. This algorithm presents a highly effective and scalable solution for merging multiple sorted lists, especially when dealing with a large datasets. So why do we need to use a min heap? By incorporating a min heap, the merging process becomes more systematic and efficient. The heap structure helps us consistently identify the smallest elements among all the lists in logarithmic time, significantly reducing the overall number of comparisons needed. Let's begin with the basics. The traditional multi-way merge algorithm is used to merge case-sorted input lists into a sorted output. This is commonly used in external sorting and large-scale data processing. However, when the data set is massive, traditional methods face performance bottlenecks in terms of time complexity, memory usage, and input and output operations. Improve efficiency of the efficient multi-way merge algorithm using a min heap. The first one is optimized for large data sets. To address these limitations, we introduce a min heap, a core data structure. Each of the case-sorted inputs in streams contributes its smallest unprocessed elements to a min heap. The min heap efficiently keeps track of the smallest elements across all inputs with order log k operations. This significantly reduces the number of comparisons needed and enhances computational efficiency. Why is this ideal for large data sets? Traditional pairwise merging scales poorly with large k values. By leveraging a min heap, we ensure logarithmic complexity in selecting the next smallest item, even when merging thousands of sorted streams. This results in consistent performance without degradation, even when a data exceeds available RAM. The next one is adaptable data variations. Another strength of this algorithm is its adaptability to various data distributions, whether the data is sorted, reverse sorted, or randomly ordered. The min heap mechanism treats them uniformly. There's no need for manual tuning or distribution-specific adjustment, which is a major advantage in real-world systems where data characteristics vary widely. The next one is the memory and input and output optimization. In order to computational efficiency, this approach is designed to optimize memory usage and input and output operations. Since the only top elements of each stream are kept in memory, the space complexity remains order of k, regardless of the total data volume. Input and output operations are minimized by processing data in blocks or pages, making it highly suitable for external memory algorithm or SSD HDD based system. Now, let's explore the three key advantages that makes this algorithm expectationally scalable and practical. First, we have the reduced operations. The min heap structure plays a crucial role here. Instead of scanning every input list for the smallest elements, the algorithm simply extracts the minimum from the heap in order log k time, where k is the number of input lists. This drastically reduces redundant comparisons and ensure the performance stays efficient even the number of inputs grows. Second is optimized merging. The algorithm only tracks the current smallest elements from each list, which means it's avoid holding all the data in memory. This minimizes memory consumption, making it suitable for all cases like external sorting where the entire datasets may not be into RAM. With fewer comparisons and less memory overhead, the merging process becomes both faster and more scalable. Third, we have the simplified implementation. Despite its powerful performance, this algorithm is relatively easy to implement. It avoids the complications of traditional multi-pass merge strategies. This simplicity is not only makes development faster, but also improves maintainability. A key benefit when working with large systems that requires consistent tuning and scaling. One of the standout advantages of the efficient multi-way merge algorithm using a min heap is it the optimized memory and input and output usage. These aspects makes it particularly valuable in scenarios involving large-scale data processing, where system resources are often a bottleneck. First, let's talk about the faster results. The min heap based algorithm combines the best aspect of multiple sorting techniques to produce faster sorting. By reducing the number of comparisons and efficiently managing data in memory, the merge operation becomes quicker than traditional sorting algorithms, especially when dealing with large or complex data sets. Next, we have the consistent performance across data sets. Whether the input data is sorted, reverse sorted, or random, this algorithm delivers reliable performance. The min heap structure ensures that the algorithm remains efficient regardless of the data distribution, meaning it doesn't require additional optimization for a specific types of data input. Finally, we come to the proven efficiency. Benchmarks have consistently shown that the efficient multi-way merge algorithm using a min heap provide a significant speed and efficiency improvements when compared to other traditional sorting algorithms. In real-world applications, it has a proven to outcome perform single-pass or multi-pass sorting techniques, making it a trusted solution for merging large datasets with minimal computational costs.
We're now going to proceed to the implementation of the multi-way merge algorithm using a min heap for optimized data merging in three main steps. In the first step, we insert the first element of each list into the heap. In this step, we initialize a min heap data structure, so the code iterates through each of the key input sorted lists. If a list is not empty, Its first element is inserted into the mean heap. Each element in the heap is represented as a tuple, which is the value, list index, and the element index. This allows the algorithm to track not only the value but also its origin list and position within that list. So the Python code showed this with the line and iteratively insert the first element of each non-empty list. The swap counter tracks the number of swaps during heapification. After this step, the heap contains the smallest element from each input list. The heap is then heapified to ensure the minimum element is always at the root. So, in line-by-line explanation of the pseudocode, this line which loop iterates through each of the k input lists, and then a crucial check to avoid errors if any list is empty, wherein we are going to use an if statement, which is the line, then the line is used to get the first element from the list, which is represented by I. In the last line of this step, which is the line, is where the core of the initialization happen. Then, the insert operation maintains the min heap property, which is maintaining the smallest element at the top. Meaning, in the second step, while heap is not empty, we extract the minimum and insert the next element. This is the main merging loop. The algorithm repeatedly extracts the minimum element from the heap, which is the smallest element among all the lists at that point. This minimum element is added to the merge list. Then, if the extracted element's originating list has more elements, the next element from that list is inserted into the heap. This maintains the invariant that the heap always contains the smallest remaining element from each list. The Python code demonstrates this with, which is represented by, and subsequent removal and replacement. And the insertion of the next element is also represented by, the heap is then heapified again to maintain the min heap property. Now, in the line-by-line explanation of the pseudocode, the first line, wherein the algorithm continues until all elements are merged, meaning the second line will then remove the smallest element, which is at the root of the min heap, and return its value, original list index, in the index within that list. And lastly, in the line, the smallest element is then added to the final sorted result list. In the last step, which is the step 3, we just need to insert the next element from the same list. This step is integrated within the step 2. After extracting the minimum element and appending it to the result, the algorithm checks if the source list from which the minimum element came has more element. If it does, the next element from that list is inserted into the heap. This ensures that the smallest element from each list is always available in the heap for the next iteration. Now, in the line-by-line explanation of the pseudocode, in the first line, the condition will check if there are more elements in the list from which the minimum element was just extracted. So in the second line, it will get the next element from that list if there are more elements. And the last line is used to insert the next element into the min heap. Here, in this slide, shows the Python implementation and a brief performance analysis. The Python code implements the step outlined in the pseudocode. It uses a list to represent the min heap and include function to perform heapify operations. The code also includes counters for swap and comparison, allowing for performance analysis. The performance analysis highlight the reduced time complexity, showing the efficiency gain of using a min heap.
Now let's move to discussing the performance analysis of efficient multi-way merge using Mhei. Let's start with the execution speed comparison. On this slide, it highlights that using a min-heap data structure improves the efficiency of merging multiple sorted lists. So what is a multi-way merge? It refers to the process of combining several sorted lists into a single sorted list. While time complexity, it is a measure of how the execution time of an algorithm increases as the size of the input grows. Now let's compare the O n k versus O n log k. O n k represents the time complexity of a less efficient approach, where n is the average number of elements in each of the k sorted lists. While on n log k, it represents the time complexity of the min heap based approach. This is significantly better, especially when the k, which is the number of lists, is large. Next is the efficiency analysis. This slide focuses on how a min heap makes element selection more efficient in a multi-way merge. When we say efficient element selection, in a multi-way merge, you need to repeatedly find the smallest element among the list being merged. In a min heap structure, it is a special tree-like data structure where the smallest element is always at the top, or in other words, the root. The O1 time naman, it means constant time. It indicates that finding the smallest element in a min heap takes the same amount of time no matter how many elements are in the heap, which means to be very fast. While eliminating comparisons, using a min heap avoids comparing all the heads or the first elements of the list each time you need the smallest one. This is because the min heap keeps track of the smallest element for you. In simpler terms, imagine you have a several sorted list of numbers and you want to merge them into one big sorted list. A min-heap is like a tool that helps you quickly find the smallest number among all the lists. Because the smallest number is always easy to find in a min-heap, the merging process becomes more efficient. You don't have to waste time comparing all the numbers at the beginning of each list. Lastly, the memory usage, which explains that using a min-heap in this algorithm is memory efficient. When we say compact heap size, the algorithm uses a min-heap and this min-heap doesn't take up a lot of extra memory. When we say OK extra space, it is a way to describe how much extra memory is needed, while K represents the number of sorted lists you're merging. So, the algorithm only needs extra memory that grows in proportion to the number of lists. If you have 10 lists, it uses a certain amount of extra memory. If you have 20 lists, it uses roughly twice as much. When we say single active element naman, the min heap only keeps track of one element from each sorted list at a time. This element is the smallest remaining element from that list. While memory-constrained environments, because it uses memory efficiently, this algorithm works well even when there isn't a lot of memory available. In simpler terms, when merging many sorted lists, the min-heap method is good because it doesn't require a lot of extra memory. The amount of extra memory it needs increases only with the number of lists you're merging. This makes it suitable for situations where memory is limited. So on this slide naman, it presents a visual representation of performance analysis likely related to an algorithm or a system. It highlights three key areas of comparison: the execution speed comparison, which shows how fast the algorithm or a system performs; the efficiency analysis, which evaluates how effectively the algorithm or system utilizes resources; and the memory usage, where This section illustrates how much memory of the algorithm or system consumes. So let's move to the next one, which is the example of execution speed comparison. The example illustrates merging four sorted logs with 10,000 entries. A traditional pairwise merge might perform 30,000 plus comparisons, while the min-heap-based algorithm maintains a heap of size 4 with O log 4 equals 2 operations per cycle. This reduces comparison complexity from OKN to ON log K, resulting in 20,000 comparisons and saving 30% processing time. The result is a greatly reduced merging time in real-time log consolidation systems. The next example that we have is the efficiency analysis. The example shows merging three lists, the list 0, 2, 8, 12, list 1, 1, 7, 15, and list 2, 3, 5, 20. Instead of scanning all lists every time, the heap structure ensures only the current minimum is compared and extracted, resulting in fewer swap operations during heap rebalancing compared to full resorting or flat merging. Testing showed 40% fewer swaps than a standard merge loop, leading to less CPU overhead and faster runtime. This is crucial for applications like merging sorted outputs in external sorting or real-time sensor data fusion. Lastly, we have the example of memory usage. The example involves merging seven sorted sublists from chunk sorting of a large file. The algorithm keeps only one element per list in the heap at a time. The heap size is 7. There is no duplication of data or temporary storage of merged results. It only appends to the final output list. This results in a memory footprint of OK instead of ON, enabling the algorithm to run in low RAM environments. So the last part that will be discussed is the conclusion, which includes the summary of efficient multi-way merge algorithm implementation using a min-heap for optimized data merging and its benefits. In this slide, it describes an efficient method for merging multiple sorted datasets. A common task in various applications, such as database systems, log processing, and external sorting. The method leverages a min-heap data structure to optimize the merging process. The algorithm operates as follows. First is initialization. The smallest element from each sorted input dataset is identified. Next is min-heap construction. These smallest elements are inserted into a min-heap. The min-heap property ensures that the smallest of these elements is always at the top root of the heap. Next is iterative merging. The algorithm iteratively performs the following steps. First, it extracts the smallest element from the root of the min-heap. This element is the smallest among all the input datasets. Next, it appends the elements to the final merge output. If the dataset from which the extracted element originated has more elements, insert the next smallest element from that dataset into the min heap. Next is termination. The process continues until the min heap is empty, at which point all elements from the input datasets have been merged into a single sorted output. Next is performance, where we have discussed the time complexity earlier. The algorithm achieves a time complexity of O n log k, where n is the total number of elements and k is the number of input datasets. This represents a significant improvement over traditional pairwise merging, which has a time complexity of OKn. Lastly is space complexity. The algorithm exhibits a space complexity of OK as it only maintains a min heap of size k and does not require additional storage for intermediate merge results. Now let's discuss the benefits. The first one that we have is faster performance. The use of a min heap enables efficient retrieval of the smallest element, leading to an overall faster merging process, particularly when dealing with a large number of input datasets. Next is lower memory usage. The algorithm's OK space complexity makes it suitable for memory-constrained environments and large datasets. Next that we have is scalability. The algorithm maintains its performance effectiveness as the number of input list increases, making it well suited for applications in cloud computing, distributed systems, and big data platforms. Lastly, reduced computational costs. The reduced number of comparisons inherent in the min-heap approach translates to lower CPU usage, improved energy efficiency, and enhanced system responsiveness. Overall, the min-heap-based algorithm provides an efficient and scalable solution for merging multiple sorted datasets. Its optimized time and space complexity, coupled with its ability to handle large datasets and function in memory-constrained environments, make it a valuable technique for a wide range of applications. So I guess that ends our discussion about the efficient multi-way merge algorithm implementation using a min-heap for optimized data merging. Thank you for listening and we hope that you learned something from us today.